niin voittikin. Jaha, okay. Let's take a look at the MATLAB and also the exercise actually. A little bit about the exercise. Just a moment. I have the. All right. So exercise 7, which is the last exercise. There's no individual exercise. Okay. No more exercises than the 7 one. So the individual exercise, I thought that okay, you have been working at least at the 5 credits worth of when we are done with this last exercise. So okay, so the first one, almost 3 credits. It's just that you can call a correct filter design program or use the FDA tool to design that filter. Okay, and as you can see, we are not talking about audio systems anymore, so its sampling rate is 1000 samples per second, meaning most probably a system controller, that kind of thing. Although this is already quite fast sampling rate for a say bigger systems, but for example, say some, well, depending on the application, of course, it could be a sampling rate for some system, and basically this is just to get some transfer function to play with, or some system to play with, and basically to find out the unit step response and the characteristics, basically, which were on this graph. So how much there is overshoot? What is the delay time? What is the rise time of this? What is the settling time for certain the value or certain range? Just a moment. I have some problems with this microphone now. Okay, so basically this is to find those values. I will give you some hints how to actually get those values from the picture, and also how to find the values on using MATLAB, some MATLAB tools. Okay, then the 5th one is paper and pen. Or actually there's also the symbolic mathematics on MATLAB. You can, or also Octave. If you define a system just like that one here, this Chebyshev first type second order system, then you can also make the transfer function of the system quite easily, actually. The same thing also on Octave, and then basically multiply that one with the step function, the Z transform, and then do the final value theorem on that one. So final value of the step response, which is the same as the DC gain of the system. And basically I also choose the Chebyshev type 1 for good reason, because it does not have unity DC gain for, well, quite obvious reason. I hate when this, yeah, thank you. So for quite obvious reason, Chebyshev second order Z-plane looks more or less like that. And basically these here define the behavior. So basically that angle is just about the same as here, but the design program gives unity gain on that spot, but this is the DC gain meaning here. Okay. All right, but anyways, basically on the parts 2 to 4, meaning it's worth of 3 points if you get everything done correctly. So whatever you get from this kind of by just doing the step response and analyzing that one, you can actually estimate the DC gain at the end of the step response when you think that it has already settled. Okay, so you get estimate of the DC gain that way, but the final value theorem actually gives you the real DC gain. There's also a shortcut on that one, but anyways. All right, so that was the analysis tools basically for systems, and there we are interested about the step responses. And then the next one would be the analyze a PID controller, meaning that you are not designing much of anything here, just analyze it with, it has some parameters taken from mostly from the sleeve method. You just do like that, and okay, those are the parameters. I checked that most of those systems would be quite stable with small numbers of SSS. Actually you would get quite long settling time and very quite short rise time, and with the big SSS numbers you would get I think it's overdamped system, meaning long settling time, long rise time. Okay. So, but anyways, that's the control system. You have the parameters. First is to calculate the corresponding equivalent controller transfer function as a single rational polynomial. This is giving this form that it has some value plus z, let's see, plus the kd times z minus 1 divided by z plus ki times z divided by z minus 1. So it has the separate terms, and then basically you can do it also with a pen and paper, basically to calculate what is the corresponding this kind of the transfer function, which has here the b0 plus b1. Let's put it other way around. b0 z2 2, maybe like that. b1 z plus b2 divided by a0 z2 plus a1 z plus a2, something like that. Although this would be first order system on the denominator term. Okay, so this form of rational polynomial, which is quite simple actually when you do it with say some of the tools we have. Okay, then 7 and 8 is to apply this controller in a closed loop controlling loop. So basically there are a couple of parameters, and there's the plant is a simple heater block, meaning there are basically a system which has two real poles. On the discrete time presentation, the poles would be somewhere in here, just giving the kind of damping factors for the system. So the slowness of the system is defined by the pole locations. But still simple system, no oscillating poles. meaning the poles would be somewhere here, they would start oscillating. Here it's just a gain on DC term, meaning it's just a slowness of the system. All right, and to make it a little bit easier, this closed loop transfer function, when the feedback is unity, meaning that we are measuring just the parameters, the output parameter directly, no transfer functions there in between, and no disturbance. And then after doing the transfer function, it's quite straightforward what to do again, the unit step response for the control loop system. And the same parameters as for on the first part. And then basically the last one is kind of, well, tweaking the terms. Adjust the controller parameters somehow to obtain better rise time, settling time, and smaller overshoot. Meaning that you have to just fiddle a little bit with the terms and calculate the transfer function and try to find out, did it go better or worse. Okay, so let's take a closer look at this. Design the following filter. I'm not designing exactly the same filter, I'm designing something else. A system just for fun. And I'll start designing this way. Just put a couple of poles quite close to the unit circle. Maybe that's not. I will just adjust this a little bit closer. Since this would closer these are, more you have ringing. This is the kind of the fundamental frequency of the system. And then let's see, let me kill the ringing somewhere there. Say pi over 3, plus minus pi over 3 angle, and this would be is this pi over 12? Maybe. This distance is about 0.2. Let's see what happens. So I will start with the zero pole plane and just zeros and poles, and so 0 locations, j divided by 3 times 1 minus 1, right, times pi. Right, let's see, just for fun. Did I get them even close? Oh, no, 2 pi over 3, sorry, of course. 2 times pi over 3. Yeah, there, better. Okay. Pi over pi, that's really half of pi, so this is pi over 6. Sorry about that one. Now it would look more or less there. So poles actually are at range 0.8 times the exponential of j times pi divided by 6 times 1 minus 1. Okay, that's the complex conjugate pair there, and then basically let's see, z plane, oops, z plane, zzpp. Okay, that's our system. Looks Looks like that. A little bit better though. So I don't care about anything else. This is the system zeros and poles. I don't care about the gain either, since I also want to show about the zero. What is that? Where this one actually settles to. So basically, next thing would be the corresponding system parameters. So B, oops, system parameters. So B parameters are the polynomial coefficients of a polynomial defined by these zero locations. Yep, 1, 1, 1. That's great. And then the AA equals polynomial divided by the poles. Yep. So those are the system coefficients. Second order system. And next, let's try the step response. I'll take 100 points at the beginning. This is just, I have no idea how fast this was settled, so I cannot say for sure if this one settles already below that 2% level error margin. This is just testing. I start with 100 points, and I start the indexing before the point 0, just to make a better looking graphs. Okay, just the first region of interest. If this one goes sour, I can easily actually go back and start doing it over. And then the step function is, well, you should know that one, and greater than or equal to 0. Step function, and then we have a system parameters, linear system parameters. So now we can calculate the step response simply by filtering the unit step. Yeah. Unit step response is there, and we can stem it. Stem NN and UU, not UU, SS. There. Ooh, wow. Excellent. So this actually will settle faster than this original. So in this case, the settle, let's see, the final value would be more or less the last point here. So it has definitely to be settled within 2%. So within 2% accuracy, we can say that is the final value, but not better than that. This is just a guess. Okay, so let's start with the so the final value, or the DC gain. Roughly. Oops. The last point on SS. So that's the last point we recalculated. Okay, 11.79. That's the estimate for DC gain. All right. Next one would be the calculating the rise time and delay time. And now we know, okay, that's our final value is just around there, so that 90% is then related to this value. All right, so 90% of final value is, let's see, V90. No, that sounds Volvo. L90. L 90% basically it's the same as the well, let's see. Hmm? Yeah, I know. Let me first, if v equals that one, that's the final value, and then we have if v90, 0.9 times fv. That's the 90% rise time value. Okay, and then we have the also fv10, which is just 10% of the final value. There we go, and basically now we can plot those lines here. I just do this one guesstimating from graph. So line x, for example, from -10 to, or minimum of indexes to maximum of indexes, and then the vector 1 1 times fv90. All right, and color is blue, red. All right, there we go. That's the 90% rise time. Oh, it looks like 0 1 2 3. So the rise time is 3 time steps. This is discrete time system, so we have just integer values for, or quantized values for rise time. If this was a continuous time system, then you need to find the value for the continuous rise time signal. But discrete time systems, discrete time everything. Okay, so it looks like rise time equals to 3 time steps. If we now knew the sampling rate, which is, for example, 1 kilohertz, this would be 3 milliseconds. Okay. And then the another line is 10 green. Okay. So rise time is more or less, it's not 0, it's actually 1. Rise time cannot be 0. So linear estimation actually would give you some 0 point something, but as remember, time is quantized here. It's sampled signal, sampled system. Rise time 0, no, the delay time is not 0 because this is less than 10%. So looks like delay time equals 1 time step. It could be actually also 0 delay. 0 delay system makes also some sort of sense. All right, next, the overshoot. Overshoot percentage. For that one, we actually find the maximum value. Maximum of maximum of SS. Yes, thank you. And this is not the value. The overshoot was percentage over the DC gain. So basically the overshoot is mm minus that DC gain was FV divided by FV times 100. So it's basically in percent. 24% overshoot. Okay, makes kind of sort of sense. Okay, and then the settling time. For that one, actually, we need to take a look at the plus minus 2% in this exercise. All right, so let's calculate. Well, I'll just add more lines here times FV times 1.02. That's the 2% plus, where's plus 2% line. Okay, green, maybe magenta there. And then of course we need to also put the minus 2% line here. And there, let's zoom it a little bit. From, let's see, maybe 0 to 20, and from okay, 12 to 14 maybe. Okay, so the question is at which time the basically this oscillating signal goes the last point which is outside of the region. So that's a point outside of the plus minus 2% region, with this one here. So that's the last point. So one after that, that's the settling time. Now the signal has settled, since after this one you don't get any overshooting more than 2% there anymore. Okay. So in this case, so after, okay, so n equals 14 is the last point where signal goes beyond plus minus 2% region, meaning that the settling time for 2% is then 15 time steps. Okay. So we have well, first of all was the same system, but you have a different system. Then basically calculate the unit step response, stem plot it, and start looking for different values. They're basically the roughly the last point of SS, meaning that you must actually observe that the signal has settled enough. What is enough? Well, this is basically, this is not science, this is engineering. Okay, and then you can actually, well, eyeball that value. Eyeballing this value does not affect that much on 90% value of 90% rise time. 90% is, it doesn't matter if it's 90% or 90.1% rise time. It's still the same. It's a discrete time system, so it still is the basically the next value where the signal has rised that 90%. Then the delay time is defined as the when the signal reaches 10% of the final value. All right, so overshoot is basically the percentage of how much the signal goes over the over this final value. That's the maximum signal, and percentage using the reference point is reference level is the DC gain. DC gain was just that final value, and then this the settling time for 2%, you just look between the lines. Yeah, something like that. Okay, good. So that's the first part. Then the second part, just to amuse ourselves about the final value theorem. Let's take a quick look at what the final value theorem actually was. Okay, final value theorem says that, okay, it's the same thing. Oops. If you want to find the last point, well, the point where this one is going to, z minus 1 or z, and then this is a z transform of this x of n. Okay, z goes to 1. All right, so basically now our signal is the same as the system step response. Yes, because we are actually interested about the how this guy actually is acting. So how the this one is going and settling into some certain value. We are not interested in any other. Okay, so basically what we need to know is first what is the z transform of step function. I think I actually added a link to, well, let's see, z transform of unit step function. Wow, unit step function. Wow, it's actually funny. It's the z transform of unit step looks like z divided by z minus 1. So actually what happens to this one, so to get the limit, this limit value of Sn as n reaches infinity is the same as the limit value of z approaching 1 for h of z. Right. Correct? Maybe. Okay, this is actually a little bit easier than it looks like, the limit value theorem in this case. On the other hand, for this would be a little bit more interesting if you want to make a the final value of some other than unit step response. Then it comes a little bit different. For example, ramp response would be one quite interesting. What happens, for example, for the what is it? The auto drive, the speed, what is that? Speed control on car when you hit a slope. Does it start falling behind and then accelerate, falling behind, accelerate, as it did on the cars on 70s and 80s and even on 90s? You have still these speed control systems that start oscillating when you hit a slope. Okay. Bad design for PID control. Alrighty then. Okay, so it's basically limit z to z approaches 1, which is quite simple in our case. If you don't have any poles here, so this is actually what that one says. If you don't have any poles, then you just calculate the value at that point. If you have a pole at this point, as you may have in control systems, then you actually need to take the limit, meaning approaching to the point in, well, one of the sides. This is simply h with value 1. Okay, that's quite simple. We have polynomial on the top and bottom, and then the c is actually c squared is still 1. So upstairs we would have bb times z to times 1 to no 1 times 1 to power of 2, 1 plus 1 times 1 to power of 1, and plus 1. So the upstairs is 3. Similar way the downstairs. You always have the just the sum of terms. Sum of terms works if the denominator does not have special point pole on the unit circle. Control systems usually do have. That's the pole for derivative. Yes. Z divided by z minus 1 has a special point there. But in this case, it's basically just easy again. Sum of those terms divided by sum of those terms. 11.7943, and how much did we calculate it in here? It was 11 point, well, it's quite the same, 11.7943. Let's see what is the difference here for the rough brute force method and this final value theorem. So dc g minus fv. Okay, that's the difference to the brute force approach. Okay, negligible, I would say. But we were kind of lucky.
Why can't you just sum all the AA coefficients to each other and you don't have to compute to, it's 1 to the power or something?
Yes, exactly. So this h of z, it's b0 z squared plus b1 z theta plus b2 divided by a0 z squared plus b, not b, a1z plus a2, and here z equals 1. So it's actually the b0 plus b1 plus b2 divided by a0 plus a1 plus a2, which is the sum of terms. Dirty trick. All right, so that's one way of doing it. Anyways, let's take a closer look at now how to actually present this system so that you can do some funny calculus with say in symbolic tools. All right, so yeah, it's funny calculus. Ha ha ha. Okay, first let's make this one a object, basically a system object or transfer function object, and in MATLAB there's a command tf. TF, create transfer function model, convert to transfer function model. So basically, if you just make a system equals to TF numerator, comma denominator, and those are the numerator and denominator coefficients a and b, or b and a. But anyways, it looks a little bit different. Now it has quite nice tools. The MATLAB and also Octave actually also have these same fundamental tools to present these transfer functions so that they would look like transfer functions. This far we have been having just these coefficients, and you have to kind of imagine the transfer function yourself. No more. So system, for example, what was this system? That was my system. My system. Equals transfer function divided by numerator is bb, denominator is aa. Okay, if I knew the sampling rate, I could actually put it here. And hopefully it understands that this is a discrete time. Oh, it gave me continuous time system. Let's see. I think I need to tell it that this is a this is actually a z transfer function. So like this. Oh, no. Okay. I will put the sampling rate here. That should work. Yes. Discrete time. In Octave, actually, you don't need to define it separately as a discrete time. That's a default is. In Octave, it's a discrete time. In MATLAB, for some reason, it's the continuous time. Okay. But anyways, now, well, that looks like a transfer function. What else did it actually give me is the okay, all the information of the system. So it looks like that. And what is the best part of it? Basically, you can now do also the parallel or cascaded systems. For example, if you have this system and another MySys 2, for example, would be TF of 101, and then let's see, 1 0 0.2 0.3, I think. Okay, 1000. That transfer function is, well, like that. Now we can combine. So parallel systems, I need to put it like this. Yes, I can actually calculate the transfer function of parallel systems. The total would be just parallel minus 2. Okay. That's how easy it is actually to start playing with these numbers. It's just, you know, it's just a variable. But it's a transfer function variable in MATLAB space. If you want to get the numerator and denominator back, so you can do the, for example, the step response or impulse response of frequency response, you can get it like this one. Numerator equals to minus parameter numerator. And I think I need to also do the cell to value cell. Let's see what happens. No. Let's see. Back to here. TF is all right. I wonder how to get it back to the step. Can we use actually this model directly? Oh, I see. You can actually do it directly with the some of the functions. Why doesn't it have properties? No, okay. Oh, not. It's just simple num and then. By the way, there seems to be a little bit difference between the Octave and MATLAB, how they handle these transfer functions. If we are using Octave, read the SELP files quite well to see what is the format. But anyways, now we have numerator, denominator, which means that we can, for example, see what are the zeros and poles, which are basically numerator and denominator, like that. So, oops, what happened? Yeah, of course, they are cell variables. I hate when that happens. Yeah, I think there's supposed to be something like this. Let's see, help. Cell to array. Cell to array. No. Matrix. Yes, cell to matrix. Okay, much better. The this is one of the improvements that I didn't want to happen on MATLAB. It actually started using cells which can consist of well, it's similar to say JSON scripts and that kind of things, where you can inside of one block you can start building different kind of variables within one cell, which is totally useless piece of garbage. In my humble opinion. All right, now I can do those. All right, that's zero pole plot. And zero pole plot shows this is a stable system. Then we can do, for example, the frequency response. There we go. So that's the frequency response of the parallel system, and you can also do the step response and whatever. So basically that's how you fiddle between different kind of the representations of the system. So transfer function as a transfer function object. You build it with TF from numerator coefficients and denominator coefficients, and adding there the sampling rate actually gives you a system, the z-plane transfers system transfer function. Okay, then the you get back to the parameter, back to the parameters by this funny. So this this field, num field in this object actually is a cell array that you can actually then transfer to back to matrix, the meaning array of values, which you can use on our frets or whatever filter or some other command. Okay, but you can do the analysis of the system on these symbolic transfer functions. The same way the cascaded system so if we had a cascaded that would be just multiplication. Let me try something here. I think I can do my sys times my sys2. Yoo-hoo! So that is the cascaded system. Okay, how about feedback system? Plant and feedback. So my sys is the plant and feedback would be the the other one, my sys2. H of z equals, I think was g of z divided by 1 plus f of z times g of z. I think I can just write it down like that one. My sys feedback equals to g of c is our my sys divided by 1 plus the my sys2 times my sys. With some luck it works. Ooh, wow! 6th order system as a feedback system. And then you can do the parameters, take the parameters out, and do the analysis of how this one actually behaves. Okay, so the nice thing about the symbolic part is that you can just do the calculations with the symbolics and then just go and do the rest on the ordinary method what you can already what you already know how to use them. Frets, step response, that kind of stuff. All right, so let me take a quick look on the exercise. Okay, that was that part. Yep, some fun. PID controller. Okay, see there's some parallel systems. Then there's the plant transfer function, and there's a feedback system. So basically this 7 to 8 is the closed loop transfer function meaning you just put those values in, calculate the loopback reduction, or actually these are cascaded, parallel systems, cascaded systems, loop back, and that the whole system transfer function. And then use that transfer function to figure out rise time, delay time, overshoot, settling time, DC gain. Okay, and finally, my suggestion is actually when you do this analysis here, have everything, since basically finally you will start filling these values. If I were you, I would actually start making a let's see where to overshoot, funny calculus. All right, so let's make a for example, run it first once, the analysis loop, run it once, oops, so that you have a working analysis loop. Then create script, and there start fiddling with this KD, KI, and KP values, one at a time. See how they actually affect on the step response. Do you get, when you multiply, when you are adding some gain on the proportional part, what is the effect? I would guess the rise time will be better. I'm also guessing that the overshoot be higher. Then you think, okay, if I got something now correct, okay, overshoot value actually, I think it's because of the derivative term is not high enough. Maybe. But one by one fiddle the K, P and I, or P, I, or D, or B, I, and D, PID values one by one, so that you get basically, as I asked there, I'm just asking better rise time, better settling time, and smaller overshoot. I'm not telling how much better. You can define it yourself. Yes, the question.
Do you need to get them all at the same time? Can you fiddle with them at some point you have better settling time and then
Let's see.
different settings you have first?
There's one word that tells you that one. And. Okay, so all of those terms must be better at the same time. Yes. Okay. Question.
So for calculating the systems, can we use z as a variable?
I think you can.
Because I'm not quite sure how to
Yeah.
use the
So-
z terms in exercises.
Hmm?
I'm not quite sure how to use the z terms in tasks.
There is a way to evaluate that polynomial or rational polynomial by setting the z equals to something. Oh yes. That's for something for you to find out. Hey. You can. Yes, you can. Any other questions? Okay, if not, then start working. So this was the last lecture and tutorial. Number 7. So next week I don't is this I think the laboratories is free to use, or any other laboratory will be free to use. I'm not here. I will be somewhere else, hopefully. But yeah, thank you for tolerating my humor. And then I will start going through the exercises, so say tomorrow or something like that. So if you haven't returned exercises by deadline, I think the deadline for number 6 was today. Okay. Yeah. it basically was, but I'm not putting any penalty until I have myself started checking them. So why I should actually ask you know, start penalizing something that I cannot you know, keep up either. So kind of my philosophy. And then actually the as I said, told you about the results. There's the scoreboard. 40% is 1 and 90% is 5. Yes.
What happens if you get 100%?
5.
So there's no reason to get 100%.
It's
Well,
90% of the work.
Yeah.
10% of the time.
Yeah, there must be always some, you know, error margin on the this grade. So it's 90% to 100%.
Yeah, it's not good to over-engineer if you're
Yeah.
an engineer. So 90% is not enough.
Okay, good. So start working. If you have any questions, ask today or send me email.